Hello, my name is Nicholas, and in this video I will be showing you the rain particle system that I developed as part of a final year university project. I'll be talking a little bit about how the rain particle system works, what some of the advantages and disadvantages are, what some potential optimization and efficiency improvements could be, and I will show you the 2D platformer game in which this was implemented. What you're looking at now is the development environment for the rain system. We can see rain particles spawning near the top of the screen, falling down towards the bottom, and where they come into contact with these red surfaces, they are becoming deleted. What this means is the weather system is able to create rain which accurately reflects the terrain or the level geometry which it is given, and we can have areas underneath surfaces, roofs, caves, which are sheltered from that rain. Basically, how the system works is that the weather system itself has one large bounding box which defines where the weather is allowed to exist. In addition to that bounding box, for every surface within the weather system's area of effect, it creates another bounding box which reflects where that surface is. What this means is that each surface has its own bounding box associated for collision checking with the raindrops. When raindrops are inside either the storm's area of effect or inside a bounding box associated with a particular surface, the raindrops are permitted to exist and continue falling. As soon as those raindrops fall outside of those bounding boxes, i.e. when they crash into the surfaces, they are removed, which gives us these areas underneath the surfaces. The use of these bounding boxes means that each rain particle is only ever performing one collision containment check per update. That is, they check whether or not they are inside the area of the storm which they are permitted to be in. If they are, they exist. If they are not, they are deleted. What this also means is that other objects within the game environment, to detect whether or not they are in the rain, can perform collision checking on the same set of collision boxes. So how does it work? The rain system, for each surface that it sees, I will briefly disable these two. For every surface that it sees, it will create a bounding box which represents the area directly above that surface. This bounding box here, for example, shows where rain is allowed to exist above this particular surface. If we were using simple geometry, which only worked on a grid system, a basic rectangle would be enough. Because this system also takes into account angles, the system utilizes a quad, which is a 4-point shape. When rain particles are spawned, based on where they are in the storm, if they are within the quad of a particular surface, that quad is then set as that raindrop's parent. What this means is that that raindrop will perform collision checking against this quad which has been created, and as I said before, whenever it falls outside of that quad, it knows it's hit a surface, and so it deletes itself. When there are multiple surfaces, multiple quads are created, and the system is intelligent enough to detect the overlap of quads and constrain them such that we aren't saving redundant data about surfaces which are obscured. In this particular scenario, we've got a partial quad being created because the surface below is partially obscured. And if we have surfaces which are completely obscured, they are completely ignored by the rain system. This works with multiple surfaces, and what we can see here is a typical example where we've got these red lines representing level geometry, and we have a series of quads and partial quads which make up the area where the rain is allowed to exist. As soon as the rain falls outside of these areas, for example anywhere under the surfaces, it gets deleted. This also means that when our character or other objects in the game are moving through this environment, they can check whether or not they are within these boxes to determine whether or not they are affected by the rain. For example, should they be wet, should their movement be slowed, should they suffer the effects of cold, these sorts of things. Because we are using quads, the collision detection is a little more complex than simple rectangles, so each quad is divided up into a pair of triangles. What then happens is a point in triangle containment checking algorithm is used to determine whether the raindrops are inside either triangle making up the quad. This is more or less how the system works. The environment in which it was intended to be used is that of a 2D platforming game, something like Mario or similar titles. In terms of efficiency, each particle is only ever performing 2 collision checks, one for each triangle making up its parent quad, per update. This makes it much more efficient than every raindrop performing a separate collision check for every surface making up the level geometry. And it allows the level geometry to be changed, and the rain system is able to update and take into account where those surfaces are by updating the quads. In terms of improvements that could be made, firstly, the system doesn't take into account overlap of surfaces in the y-axis. What this means is, as you're seeing here, this surface is considered to be lower than this surface because this surface has a higher point. What this means is it assumes that this surface is in fact below the other surface, and so only creates a partial quad, when in fact what is happening is this surface is partially, in fact, over top of the other surface. This isn't too serious of a problem, because simply keeping track of how you're creating your level geometry will mean that this situation will very rarely occur. It is, however, quite interesting to see the effects of this Y overlapping process. What this means is you will avoid scenarios where potentially platforms which should be blocking the rain aren't, or when small changes in the level geometry will produce vast changes in where the rain is and isn't allowed to be. The second improvement which could be made is just a general particle system optimization, and that is using a pool design for the particles. Rather than creating new particles and deleting particles every time they enter or leave the area of influence, you create a whole bunch of particles and then recycle them. This makes the system more efficient and run smoothly because you're not constantly allocating and freeing up memory. In terms of memory management, because this is written using C# in the XNA game framework, things like references and pointers aren't utilized or used to their full effect. And I believe this is partly the reason why when surfaces are moved, the rain takes some time to update to reflect those changes. For example, if I move this surface upwards, you will notice that rain will still fall underneath and through that surface to where it used to be for a short time. I believe the reason for this is that once raindrops are created, they store a copy of their bounding area rather than referring back to the weather system's updating copy of bounding quad. Meaning that when the level geometry changes, it takes until new raindrops are spawned for those changes to be reflected as the old raindrops continue to reflect the old level geometry. So this is the rain system, this is sort of how it works, and this is the development environment in which it was built. What I'm going to do now is swap over to the 2D platformer game that I developed as part of this university project, and show you it in action, if you will, within a game environment. So the game that we developed made use of a simple level editor, which you can see here. And the idea behind using surfaces is basically that you can have a very complex visual background to your game while still maintaining a very simple set of surfaces and lines for which the program will actually perform physics and collision checks. So what you can see here is I'm drawing on the surfaces to this background. And these are basically the surfaces that the weather system would be taking into account when determining where rain should or shouldn't be. And you can see that even with a complex background, I can very quickly draw on these surfaces, and then when the game is performing collision checks, physics simulations, and these sorts of things, it's got a very simplistic and minimalist view of the environment against which to be performing these calculations, rather than having to take into account anything like the complex graphics which you're seeing here. So this is the level editor in which the levels were made for our 2D game. I will now start up the game and you will see how it looks in action with the rain. So this is the game. What you can see is that same level that we were talking about. And we can see our rain system in effect. What's happening here is that this little alcove is sheltered from the rain. And we can see that those surfaces we defined earlier are being used for the physics and collision checking and pathfinding of the enemy AIs and such. And as we fall down here, we can see that these areas are sheltered from the rain. As I mentioned before, one of the benefits of using these bounding quads to define where the rain is and isn't affecting means that our character can perform very simple collision checks on those boundaries to determine whether they are in the effect of the rain. Rather than checking against each rain particle, it can check against all those bounding quads and determine that here it is not inside the effect of the rain, and here it is. And this can be used to trigger cold effects, to change sprites to reflect the fact that they are wet, and other things like that. This video has been a demonstration of the rain particle system I developed. Hope you have enjoyed. Please leave any comments or queries in the comment section down below, and check out my channel for videos on this and other projects. I hope you have enjoyed. I'll see you next time.